Hi there. Today we'll look at NÜWA, Visual Synthesis Pre-Training for Neural Visual World Creation. This is by researchers of Microsoft Research Asia and Peking University. The paper presents a model that can support a wide variety of image generation tasks, such as text to image, where you give a piece of text and you get an image. This is a dog with goggles staring at the camera. Up to something like video manipulation, where you want to change the frames of a video according to a piece of text. For example, the car is reversing instead of the car is driving forward. Now, you see there's not always text in the loop. Sometimes it's just an image, sometimes it's a sketch, sometimes it's just a video. So all of these kinds of tasks are supported by this model. And this paper goes into how the model's architecture is done, specifically how a transformer architecture, essentially an attention mechanism, is able to handle such large data points, essentially contexts not only going to images, but beyond images to multiple frames of video.
Heyo, this video is sponsored by ClearML. ClearML is an MLOps stack that is fully open source. It can do experiment tracking, experiment orchestration, deployment. It has model and feature stores. It is a complete package of ML tools. Now, what I want to highlight in particular here is this self-hosted tier. Self-hosted is a first-class citizen for ClearML. Everything's open source, therefore you can look at it, you can audit it, you can extend it however you want, and you can host it on your servers. There's also a free tier that is available in the cloud, so you can get started with whatever you need in the cloud, and then once you need more features, you can go to a more professional setup if you don't want to self-host. If you love open source, then ClearML might be the way to go. It is an end-to-end stack from experimentation all the way to serving. It's vertically integrated, makes your life a whole lot easier, and it is appropriate whether you are an individual running experiments or an entire team. Now, one of the core pieces of ClearML is of course their experiment tracker. It's super easy to set up. It needs like a single line of code. I guess that's 2 lines, but you know, who cares? It integrates with pretty much any tool there is. And not only does it record your metrics like you're used to, it also fully grabs all the console output of your experiments. It grabs any artifacts that the run might have produced. And most importantly, it clearly records not only your hyperparameters, but also the other parameters of your environment, such as the path and the machine you ran it on and your dependencies. Another really cool feature is that it allows you to compare different experiments. For example, here it shows you what part of their configuration was different. So you're able to pretty quickly figure out what made the difference in any particular run. And of course, you can grab a bunch of experiments together and then analyze them next to each other. So now there's no excuse anymore for blaming your tools. Any fault in your machine learning project will be yours and yours alone if you use ClearML. Isn't that a promise? So I invite you to go over and check it out at clear.ml. And thanks so much to ClearML for sponsoring this video, and let's get into it.
So yeah, we'll go into the paper, we'll see how they do it. I do find this opening thing right here is a little bit overstated, because a lot of these things aren't coming out of the same model, but the model is then fine-tuned on different things. And I also find the paper is a bit unclear on some of the details. And if I understand correctly, there is no code yet that we can look at. Maybe that's going to be released, maybe not, who knows. To the name NÜWA is, there's this umlaut, which we do have in German, but I don't believe this is a German inspired name or any sort of Nordic language. I do believe this comes from the symbol in Pinyin that is represented as an umlaut on the U. It took me like so long to figure out that you have to type a V in Pinyin to get that output. I just couldn't spell words like nü for a long time, but now I can. So I do believe this is pronounced NÜWA, but correct me if I'm wrong. Also, many thanks to Andreas, who helped me prepare this paper a little bit. gave me some inputs. This is very much appreciated. Follow Andreas on Twitter. He also often posts updates for our paper discussions on Discord. So very helpful. Thank you. All right, let's get into it. So this model is something like an image GPT model. If you know image GPT is essentially similar like a pixel RNN, where you have an image and you want to produce the image sort of pixel by pixel, left to right, top to bottom. You produce just one pixel after another, after another, after another, and you learn this how you would learn a language model, essentially, just pixel by pixel. And you can support tasks like completing images, where you simply give everything here you already set pre-computed, and you simply let the model infer these pixels right here. Or you can support things like image manipulation by simply, you have a picture right here, and or let's say that's the cat, and you simply cut out part of the image. So you cut out this part or something, you let the model fill it in. So you could do things like in painting or something like this. This is supported by image GPT. Now the problem with something like image GPT is that if you want to have this as sort of a language generation task, then your context size is, if you predict the pixel on the bottom right here, the context is like all the pixels in the rest of the image that you've already generated. And if you have something like a 200 by 200 image, that is 4,000 previous pixels. Now 4,000 is just about, no, is it? It's 40,000. sorry about that. 40,000. That is definitely outside of the scope of every transformer that we have. And beyond that, if we now look at video, and video is essentially just a stack of images, right? So you have an image frame, the next frame, and the next frame. If you look at that, if you want to produce a single pixel right here, not only do you have to take into account all of the pixels of the image that you've generated so far, but also all of the pixels of the previous frames that you've generated so far, right? And that definitely blows the context of any transformer. That is infeasible. So this model here very much is about how do we make this feasible? The answer is going to be twofold. First of all, we're going to encode all of the data into a common space that is kind of discrete in latent space and is way less dimensional. And the second answer is going to be we're going to use local attention in order to work in this latent space and finally generate the output. So this is an overview over the model. I do find it a little bit lacking as a picture, but you can see that in general we use these encoders, and the encoders, they take care of bringing the data, whatever the data is, into a common representation right here. The common representation is going to be essentially a three-dimensional cube where each element is an embedding vector. But we're going to look at that now. So how do we encode text? Our goal is going to be to have a latent space, to have an encoder for any kind of data. And after the encoder, the data should be in sort of a latent space, and that latent space should be, if possible, kind of discrete or quantized. And we're going to use some methods that already exist. But for text, that's pretty easy. For text, the encoder is simply, it can be the identity function, right? Because if I have a piece of text like a cat, whatever, if I tokenize that text, that is already tokens. So right now, if we do language modeling or any sort of language processing, the first step is tokenizing the text and then associating each token with an embedding vector. So this is going to be nice. It's going to be a set or a sequence of tokens, and that's exactly the representation that we want. So for text, everything's good. We have a sequence of tokens. We have a code book, usually, which is sometimes in language modeling, that's called the embedding matrix that's at the beginning of the model. So every code vector, every token is associated with a vector. So we can look up that vector in the code book, replace the token by the vector, and then process the tokens as vector embeddings in the subsequent model. We want to do the same with images, right? We want to get an image and we want to bring it into the latent space as a set of discrete quantized tokens. Luckily, there is a technique how you can do that, and that's called VQVAE. So if I have an image, let's say, again, our cat, what I want to do is I want to have an encoder such that it results in a set of latent tokens. Now, a VQVA is interesting because what the result is going to be, it's going to be like an image, but that image is going to be very low dimensional. So here we may have 200 by 200, but over here, in this case, we have like 3 by 3. And these aren't, in fact, pixels, but they are tokens. So these will be vector quantized. There will be a code book, they call it B, and that code book will be vectors for each token. And what the encoder does is it essentially reduces the image down to a representation that is 3 by 3. And then every single pixel in that 3 by 3 matrix, every single entry right here, is going to be clamped to the nearest entry in the code book. That's the quantization step. If you don't know much about this, you can look up vector quantized anything pretty much, but vector quantized VAE is sort of the main reference right here. It's the encoder encodes in a continuous fashion, and then there is a discontinuous step, a discrete step, where we say, okay, there's latent space, and we have this code book vectors here, and they're going to live in that latent space as vectors, as points in that latent space. And if my encoder encodes an image, and I take any pixel right here, and that pixel might come to be here, I don't use the pixel, or I don't use this latent token as is. I'm going to clamp it to the value directly of that codebook vector. So all I end up with is a selection of these codebook vectors. So at each point here, there will be one of those codebook vectors, and I can equivalently say, if I like number them, this is 1, 2, 3, 4, I can equivalently say these are essentially tokens. So token 1 might be, this might be 1, this might be 2 and 2, 3, 4, 4, 4, 4, right? And from this, I can then have a decoder again that produces back an image, and the image of course is now only produced from this latent encoding. You might think that is way restrictive, but it actually turns out to be very, very powerful. So instead of using the exact encoding, we use the quantized encoding. And if our code book is large enough, you can encode quite a number of things. Like if you have 1,000 tokens, you can imagine token 1 could be, there's kind of a tree, and token 2 is like a tree stump, and token 3 is like, well, a tree that is like has needles, like a needle, like a pine, and so on. And then your latent description here just kind of roughly outlines the broad shape of the image. So not necessarily exactly what's where, but it just says like, in the top right, there's a bunch of pine trees, and in the bottom right, there's a road, and so on. So it's a latent tokenized or latent discrete tokenized representation of the image here. And you can already see that this is way beneficial because now we're only working in 9 tokens, whereas here it's 200 by 200. Now, we don't have to forget that each of these tokens obviously is going to be associated with a vector. So this is not 9-dimensional space, but it's 9 times whatever the vector dimension is that is associated with each token. As like this is not 200 by 200, it's actually 200 by 200 by 3, since every pixel has a vector of dimension 3 associated to represent color. Right. This VQ-VAE is trained as if I understand correctly, and this is the first part where the model, that the paper isn't exactly clear what happens right here. I'm not sure whether this is trained end to end or whether they train the encoder and decoder here ahead of time, because they have different formulations. They say like after training this we do that, and I'm not sure. But essentially they train it so here is how you obtain the latent representation. You send an image, that's I, through the encoder, that's E, and then you select the Z, these are the latent vectors. You select the Z or now these are the tokens, the token indices, such that you select the Z according to what's the closest vector from the codebook B. So you can see the J are the indices into the codebook. So the Z will be for token I, what ZI will be what entry in the codebook vector is closest to that representation that the encoder produced. And then the reconstructed image I hat is simply going to be, I now go with my latent representation to the codebook. I actually get out the vectors, the entries of the codebook. I shove that into the decoder, which is G, the generator, I guess, and that gives me the reconstructed image. So how am I going to train this? Well, it's easy. I want that my produced image is close to the original image right here. I also want to train the codebook, which is B, to be close to what my encoder produces. So I want the codebook to be useful, and that means the codebook needs to be able to sort of just describe the things that the encoder produces, right? So the code, I'm going to draw the codebook closer to the encoder's output right here. The SG is a stop gradient, which means that this part of the loss affects the codebook. But also we have the symmetric part right here, where we're going to teach the encoder to produce things that are better encodable by the codebook. So here the stop gradient is on the codebook, which means that this part of the loss affects the encoder. It's quite common to split up two losses, even though this could be in one loss, right? Since it's symmetric, it's quite common to split it up into two parts, each one having a stop gradient, makes things more stable. All right, so is this actually, yeah, probably. It's just a framework specifics right here. I don't think SG is a valid mathematical thing anywhere. This really refers to the stop gradient functions in TensorFlow or in PyTorch. In addition to that, they say, well, the VQ-VAE is sort of too strict a little bit. So there is an extension called VQ-GAN that changes the VQ-VAE objective a little bit. So they say they add two things right here. One is a GAN loss, which I'm going to guess is this one right here. So you can see they introduce a discriminator that discriminates between real and fake images. And I'm going to guess that that here is the loss for the discriminator, right? Because you want the discriminator to recognize real from fake, which means you need I and I hat. But I don't see the loss that would be added to the generator, because the generator's loss, I don't think that would necessarily include the true image. But I might be wrong, because yeah. So I mean, the generator would simply not care about the first part right there, even if you included it. But you know, they introduce a discriminator, which we know can help, and they also say they introduce a perceptual loss. And they simply write this down as, we're going to pass both the original image and the generated image through a CNN, and then we compare the two. This is in contrast to comparing the two images directly. As you can see, they say that this is meant to ease the exact constraints between I and I hat and focus on high-level semantic matching. I don't exactly know what these CNNs are, if they are trained as well, or if they simply take like an off-the-shelf ResNet 50, pass the images through and compare the last layers in order to say, well, I just want the latent representations to be similar. I don't actually want the images to be similar. They also don't say whether that replaces this loss up here or whether that's simply in addition to that loss. Again, we don't know. They further say that you could do the same thing for videos, right? You could train like a VQ-VAE, VQ-GAN for videos, because after all, videos are just a stack here that we saw, a stack of images. But they say that didn't work out well. So what they do is they simply treat each frame of the video as an image, and they pass each frame through this image encoder right here, and they simply stack the outputs, or they stack the latent representations. So that'd be from the first frame, then from the second frame, from the third frame, and so on. They stack them like this. And that gives you sort of a tensor. Now, keep in mind every single entry right here, for example, this entry or this entry or this entry, every single entry is associated with a vector. So this is ultimately going to end up in a 4-dimensional latent tensor that you work with. But we can represent it as a 3-dimensional tensor of tokens, where each token will be an entry in the codebook. So how is that a common representation? We saw, so the text is 1D of tokens, or 2D if you consider it as vectors. Images are 2D as tokens, but 3D as vectors. And video is 3D as tokens and 4D as vectors. How can we make sense of this? And we combine all of this by simply introducing dummy dimensions. So if you've ever in like NumPy, you index your vector, your vector x with like, I want everything, and none. Right? That's one way. You can also use the expand dims or unsqueeze in PyTorch or anything like this to make it compatible and essentially use the broadcasting functionality of the frameworks. That's essentially what they do here. They say, we have an image, we have the latent representation, we simply add the placeholder dimension of 1, since images have no temporal dimension, it's just height and width. But for videos, this 1 would be, I guess, not a 1. So if you can bring them into the same space by using dummy dimensions and broadcasting if necessary. So now everything essentially is a 4D latent tensor. You can bring in text, you can bring in images, you can bring in videos. The next thing we want to do, and again, I don't know if these are pre-trained, the encoder, decoder, or if these are trained jointly. I don't know. The next thing we want to know is, okay, right now this is simply encoding, and then if we ship the representation through the decoder, it's right. So if we ship it through the encoder and then through the decoder, it's going to result in the same image or in a very similar image, right? So here is going to be like another cat. Like, how does that help us? Obviously, there needs to be something different, right? We want an image right here. I'm going to put it through the encoder. I'm going to get its latent representation. And then we need to do something with the latent representation, get another latent representation, then decode that, and then we get some sort of a different result, right? So a different resulting image right here. So this is the same for like image completion and so on. The question obviously is what happens right here. Now, there is where the sort of the transform or the attention layers come in. Until now, we've had classic, I think these are convnets and so on, these encoders, decoders, like you would be used to if these are images. But now what we do is we have essentially a model that transforms the that transforms the latent representation to do meaningful work. Okay, so how is that done? They differentiate two things right here. They differentiate context, which is here on the left broadly, which they always or sometimes denote with large C. Context here, and as context they count things like input text or input sketches. And the reason it's context is because those things aren't output. Those things are never given incompletely. The model will never have to produce them. You always input them. Either you input them or you don't input them. But if you do input those things, it's conditioning information that the model can look at as a whole, right? You always enter the full text or the full sketch. You never enter like half a sketch. The model can't produce sketches. The model can only produce images or image frames, frames of a video. Okay. So that is, the decoder is only images. Encoders can be for text, for images, and for sketches. So the part over here, they would generally call the output Y, even if like half of it is actual input into the algorithm. So here you can see the input is the part of an image, and the output is the remaining part of that image. Or the input is the video frame, the output is the future frames, right? So yeah, so that is the output part. And this should remind you sort of the original transformer architecture. So the sequence to sequence task is you have sort of sequence 1, and that is always given in full. And then you have sequence 2 that maybe you are given nothing at all, or you're sort of given an initial token right here, or you're given kind of a prefix of what you have to generate, and then you have to go on completing sequence 2. Now, if you don't have sequence 1 at all, that's a decoder only architecture. That's also possible. You can condition on nothing, but the most general architecture has these two sequences. If you remember the original transformer, it was exactly like this, and then, wait, let me pull this down a bit, and then it had sort of a stack of attention layers here, and a stack of attention layers right here. And what you do is, within the attention blocks, you'd had like self-attention, where things attend to each other, attention here, attention, 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 and then inside this block you'd had attention also with itself, but then also you'd had layers where attention would go from the Y part, so from the output part, to the context part. So you would let the output right here in a layer collect information from the context by doing what they call cross attention. In the original transformer paper, I think it's still called cross attention right here. Both are the same operation. Both are attention operations. It's just a matter, you always have a queries and keys. Sorry, that's an E. And keys and values. If it's self-attention, all of these are generated from the same input. And if it's not self-attention, then this, for example, is generated from the Y input, and these two are generated from the context information. And that essentially means that Y is requesting information from C, so Y is attending to information in C. Okay, same thing here. What they have this layer called 3DNA. Now that's the entire layer name, is 3DNA. That is 3D nearby self-attention. Okay, so they say this is based on the previous 3D data representation. So 3D, they essentially mean 4D, but 3D tokenized, and then each token has a vector. But the 3D comes in when they discuss how they do their attention. By nearby, they essentially mean local attention. So what they're going to do is they're going to do local attention in this 3D tensor. That is, I think, what I could gather so far. They formulate this in a general way right here. So what you'll do is you'll define this for two tensors, x and c, and sometimes those are the same and sometimes not. So specifically x can be either c, in which case it's self-attention, or x can be y, in which case it is cross-attention from y to c. I guess c could also be y, in which case it is self-attention from y to y. So yeah, I'll just make it a little bit confusing right here. In any case, it's just a matter of how you compute the keys, the values, and the queries. As you can see, the queries are always computed from the entire vector tensor x. So whatever is producing the query, the entire thing is producing the query. However, for the keys and values, what you do is you define a local neighborhood. So now we care specifically about how do I produce y at location ijk. So you have to imagine we have this 3D representation, which is essentially a big cube. That cube's elements are these tokens, right? So this is, you can imagine it as a just stack of video frames, but in latent space, right? So in latent space, we have this stack of video frames, of the latent encodings of the video frames. If it's just a single image, right, you broadcast and so on. But in that case, we wonder how from this we need to produce sort of the next layer's representation, which is also going to be a cube just like it. Okay. So as much as in an attention layer, the input is a sequence of tokens, the output is a sequence of tokens as well. In this, it's the input is a cube of tokens, and the output is again a cube of tokens. So how we're going to do that? We produce the output for each location. We define a neighborhood. So if we want to predict this would be y at ijk. We're going to search ijk over here, which is going to be, I guess, right here. Okay, so this is ijk, the same location. Then we're going to define a local neighborhood around that thing. So that could be just, it's again going to be a cube like this, that is just a little bit bigger. And they are using, as far as I can tell, they're using 3 by 3 by 3 cubes right here. So they're going to define a neighborhood. And while the queries are generated from sort of the entirety right here from the entirety of the tensor, the keys and values are only going to be computed from that cube. So instead, if this is height, width, and height, no, this is S, let's call that S, the temporal dimension, and width, even though this is already in the latent space, it would still be very, very expensive to compute self-attention or cross-attention when every single element of the cube attends to every single other element, right? That's essentially what we'd have to do. In an attention layer in text, I have a sequence, and every part of the sequence is able to attend to every single other part of the sequence. That is not feasible if you have a 3D cube, even if it's in a lower dimensional latent space. So what I'm going to do is I'm going to say, okay, if I want to compute this output right here, I can only attend to a local neighborhood around this output here. So that's that. So the queries I can compute once for the whole tensor, but then I can compute the queries for the whole tensor, but if I want to produce a particular location, the only place I can attend to is the keys and values of a particular local neighborhood. So essentially that piece of the cube here can only look at the local neighborhood around its locations in order to aggregate information. that is, yeah, it's local attention, either local cross attention or local self attention. So we define the neighborhood and we produce the query for a particular location. I'm not sure if that should be x ijk or not. Not sure, but yeah, you can see that the keys and the values are certainly specific to a location. They include this neighborhood right here, this n neighborhood. The n neighborhood is defined as this set right here, which is simply what I just said, that cube. And then I compute the softmax simply as, and this is, I think this is a mistake right here. This should definitely be not here. This should definitely be here. Yeah. So I'll compute the softmax like I would the outer product between queries and keys, just in that neighborhood, and then aggregating the values according to what the softmax of the routing table gives me. And that's how I produce this output right here. Okay, so I can do that all in parallel. I can essentially produce that next tensor right here of the latent representation, and yeah, that's that. Now, I just said I produce it all. By the way, there is a, you can see that reduces the complexity from sort of this square to simply every location attending to its local neighborhood. So that reduces the complexity by quite a bit. So for every location, that's this part, I have to attend to its local neighborhood. That's this part. There's also positional encodings, as you can see right here. And what we're going to do, we're going to first have a stack of layers of self-attention for the context, like we saw in the original transformer. So we're first going to have a stack of L layers right here. And after that, we're going to have a stack of L layers here. And each of those L layers can do either self-attention or cross-attention. But as far as I can tell, it's kind of different than the original transformer, because here you can see the next layer here is produced from the last layers. And likewise here, if I produce the I, the next layer is produced from the last layers of Y, but also from cross-attention from the last layer of Y to the L layer of C, which means that it only can look at the output layer. So the arrows I've drawn here can technically not happen, but it always has to look at like the output layer up here. I guess that's a way to do it. I don't think that's the exact same thing as in the original transformer, where you'd really have, as I shown the arrows here, you'd sort of attend to the same height. I might also be wrong in this. Or it's a wrong formula right here. That is also completely possible. Now you can see there is, I've masked this, there is also this part right here. So what we're going to use is we're going to use causal attention. So we're only going to attend. I said you can do it all at the same time. You have to do a causal mask. You know, like in things like GPT, where I produce one token at a time. When I produce this token right here, I'm only allowed to look at the token that I've already produced. And that's the exact same right here. In fact, we're going to produce this representation. We're going to start like at the top left at time step 1. And we're going to produce the whole image at time step 1, pixel, or not pixel by pixel, but element by element in this representation. And then we're going to, once that is complete, that video frame, let's say we're going to go to the next step and again do it element by element. So this is really a sort of giant autoregressive model. Now you can, with causal attention, you can train at the same time, but during inference, you only actually attend to the things in front of you. This formula, in fact, doesn't exactly. I don't. Is this correct? Because here it says everything needs to be smaller, which to me would mean that, you know, if I'm, let's just make it for 2D and let's just say it's smaller I, smaller j. It's the question of if I produce this pixel right here, technically I should have access to everything up here and the row so far, right? But with this formula, what it would mean is that I have access to only whatever is to the top left of me, like this part right here. And I don't think that's the case. I think this is just sloppy notation right here. See, yeah, this denotes the generated tokens for now. That I don't think is correct to express it like this. Seems shady. It also doesn't tell us exactly in which order the pixels are produced, though I think it's first within a time step and then across time steps. So yeah, that is that. Now let's get to the training objective. So I hope you can see that this is one layer of this 3 DNA, and we have L layers here, and L I think is 24 in their models. We have L layers for the context, and then also L layers of cross and self-attention, and ultimately we end up here with the final representation. And training we can do in parallel with causal masking, but inference we have to do element by element. So that's why they praise that their model is reasonably fast, but I think it's still like 50 seconds to produce one image or something like this. And that's why. So the training objective. And here is a little bit where where again, I find it to be quite unclear. So they say they train it on 3 tasks. And if I understand correctly, they train on these 3 tasks simultaneously. So they have 3 different data sets. One is a text to image data set where you can see right here, you produce an image and you condition on text. Okay, and you can see that this lower than t simply means the elements or the tokens lower than t. And you go from t equals 1 until height times width. So it's an image, so it only has these 2 dimensions. So, and you produce, I guess, pixel by pixel. See that I don't know what does y mean here. If it's really the output y, then you have that generator here, and the generator probably doesn't go pixel by pixel. I don't know. Maybe it does. Maybe it actually does. In any case, you have these 3 tasks. So one is text to image from a data set that does that. One is video prediction, where you simply input a piece of a video here. The C here, that is like a no-op. So that is the special word none. So because, you still have to input something, but if you have no text conditioning, you simply input a dummy. And then the loss goes also over the time steps. And there is also text to video, where you'd input text and video so far, and you'd output the rest of the frames. So that is, yeah. Again, so here probably the loss doesn't necessarily go across all the time steps, since part of the video is already given. But yeah, I guess we'll have to wait for the code to see what really turns out. Most notably, you can see that the conditioning information right here is, sometimes it's video, right? Because sometimes video is kind of conditioning implicitly by us already being part of the output. But there is no, for example, sketch conditioning right here. It's always either text or nothing. And this is pre-training. So that means everything you see to do with sketch is then fine-tuned. So that was when I first saw this, I thought like, oh wow, they train these jointly, everything's joint, and then the same model can do all of these tasks. And it turns out no, actually most of these things are then fine-tuned down the line. Now they do show that the pre-training actually helps quite a bit, but you have to understand these are in fact fine-tuned. Also, you can immediately see that something like video manipulation is not actually video manipulation. Like the model doesn't care about these frames right here. that what the car is doing. The model doesn't even see this. You simply input the first frame, and then you let it generate the next frames based on this text right here. So it's not necessarily manipulation as much as I give you the beginning of a video and a piece of text, and now please predict the video based on the text. So it's a bit like this here, except you already have the first frame, if I understand correctly. But I think I do. There's really no other way, I guess. I'm not sure. Maybe they actually inputted into the context right here. But I cannot imagine that. In any case, maybe I completely misunderstand this right here. But these are the tasks. They give some implementation detail about how the latent spaces, or you can see that there's a latent space of dimension 1280. Yeah, the local neighborhood is of size 3 by 3 by 3 or 3 by 3 by 1 for images when they're lonely images, and it's the regular attention mechanism if it is text. All right, so that is it, and the next slides are results, experimental results. I want to highlight a few. So here are things they can do. They compare, for example, with DALL-E, which is a model that is explicitly trained to produce images from text, right? Whereas this model right here is sort of a multi-purpose model. And you can see that in general, either the results are comparable or better. I mean, this is at this point, it's kind of arguable. You can measure it on certain data sets. For example, here they specifically praise this picture right here, where they say, this is very clear and consistent, and this other state-of-the-art model is not as good. I do like some of these outputs right here. Playing golf on grass, the baseline model, you can see the baseline model just screws up. Though I do think there aren't many, for some tasks, there are just no baselines available because they kind of invented them themselves. But you can see that when there's baselines available, the baselines usually they don't necessarily do so well either. So in this case, doesn't really seem to be, I guess it's some kind of a human-ish thing. But this, looks fairly neat. And you can see the resolution is also bigger than the resolutions of the competitors. That's pretty cool. You can also, as I said, this is now fine-tuned, right? If you actually want the sketch to image or sketch to anything, you are going to have to fine-tune it on that data set. But if you do, you can see that the results are very, very cool, very accurate. So this is the input. I'm going to guess that green thing here is the vehicle class or even the bus class. And the outputs are pretty convincing, honestly. So if you want, you can look at the metrics yourself. They have a bunch of more examples right here. As we said, specifically things like in-painting are quite possible right now. So you can say, I want to clamp everything to the original image except this region right here. You can give a piece of conditioning text, and that together will, this is NÜWA, this is the baseline right here, will, as you can see, fill in the missing pixels in order to also match up with the text, because it's been trained on text to image data sets. Yeah, lastly, this video manipulation, which was one of the sort of appraisals of this paper right here. You can see the raw video on top. The first row is the diver is swimming to the surface. That's given to the model, so the model is asked to manipulate the video in that way. Diver is swimming to the bottom, or the diver is flying to the sky, which surprisingly the model can do as well. Now again, I think the model simply gets the first frame and then needs to continue the video. I don't think the rest of the video has given us conditioning information, but I might be wrong, right? So if I'm right, it would not necessarily be video manipulation, but more kind of like video completion conditioned on text, but still is pretty cool. All right, so yeah, they have by the way, they have a big appendix. They also compare like different local attention mechanisms. They have much more output right here. Yeah, sometimes it's very funny, but I hope the code is out soon or is already out and I just hadn't found it. As a conclusion, they present NÜWA, a unified pre-trained model that can generate new or manipulate existing images and videos for 8 visual synthesis tasks. Again, caveat here is that only very few, only like 2 or 3 of those are actually zero shot, maybe, or resulting from the pre-training. For the rest, you actually have to fine tune. Several contributions are made, including a general 3D encoder-decoder framework covering text, images, and videos at the same time. That's what we saw is possible by doing this. Essentially, it's a VQ GAN for images. For text, it's already in the correct representation, and for videos, they simply say, well, every frame is an image. So it's like, yeah, general encoder-decoder framework covering text, images, and videos is, let's say, it's a nice formulation. A nearby sparse attention mechanism that considers the nearby characteristic of both spatial and temporal axes. That is simply local attention. So this nearby sparse attention, it simply is local attention. They simply do it over the 3 axes instead of over 1 axis where local attention was originally presented. And third, comprehensive experiments on 8 synthesis tasks. Yeah, that is what they do. This is our first step towards building an AI platform to enable visual world creation and help content creators. Yeah, I can imagine that. Like models like these are going to be pretty powerful for content creators if you can essentially input arbitrary modalities and mix them together. It's going to be pretty cool. All right, so that was NÜWA. Let me know what you think, and I'll see you next time. Bye-bye.